all that we discussed before concerned the case when there is no friction, right? So, but of course, in reality, oscillations are not going to go on forever. Right? So, in real life, if say even if you have a spring mass system in the air, then at least there's going to be friction with the air, and then the magnitude of the amplitude of oscillations is going to decrease as time goes by, right? So this is modeled by introducing a damping that comes from air resistance and internal energy dissipation, right? So we the left hand side here is the force acting on the object. So now without friction, the right hand side is just Hooke's law, and if you include friction, if you consider friction, then there's going to be one more extra negative term, so which is due to friction. And then if you move everything to the left hand side, then you are going to get this equation, or alternatively it's up to you in this form, or in this form. Now in either case, it is important to see that all the coefficients of the characteristic equation are positive, right? So, and then I suggest that you pause the lecture now and you try to think what the units of gamma are and what it means for a second order linear homogeneous differential equation with constant coefficients to have positive coefficients. Okay, and now let me explain it. Now, so how do we figure out the units of gamma? So the units of this term are kilograms times, oh sorry, not this. So let me look at this. The units of this term are kilogram times, well, that's units of mass, and units of u double prime are units of acceleration, so they're meters per second square. But of course, if you add three terms together, then the units of each term should be the same. So which means that the units here should be the same. And the units here are the units of gamma, which we don't know, times the units of u prime, and the units of u prime are meters per second. Now, in order for this to make sense, the units of both of them should be the same. So in order for this to be the same, I need to write kilograms per second here, right? So which means that the units of gamma, the units of the damping constant, are kilograms per second, whatever that means. Okay. Now, so if a differential equation has all positive coefficients, second order differential equations has all positive coefficients, what does it mean? Now, this means that the sum of the two roots is going to be a positive number, so that's G over L is positive, and then the product, no, that's the product of the two roots. So the product of the two roots is going to be a positive number, so which means that these two roots are either real numbers with the same sign, or they may be complex numbers. And the sum of the two roots is minus gamma over m, which is a negative number, right? So, and since the sum is a negative number, it means that either both of them are negative, because we cannot have one positive, one negative, because if we had one positive, one negative, then the product would be negative. So we may have two negative real roots, or we may have two complex roots with a negative real part, because if we have two complex conjugate roots, then their sum is, when we add them together, then the complex part cancels and only the real part remains, and the real part is negative, and at the same time the real part goes into the exponential function. So in any case, in our solution, we are going to have an exponential function with a negative exponent, so which means that the positive coefficients imply that the limit of all solutions when t approaches infinity is 0. That's this is what the fact that coefficients are positive tell us, which makes sense, right? Because we are trying to model real oscillations, and of course in real life oscillations are going to decay and are going to disappear, so we expect that this is going to happen, that the limit of all oscillations is going to be 0. Okay, now there's going to be 3 essentially different cases here. So the first case, positive discriminant, so then we are going to have real solutions, and this case is called overdamping. And then when the discriminant is 0, this case is called critical damping, and when the discriminant is negative, then this is called oscillations, damped oscillations. Well, I'm not going to do it, but I suggest that you click here to see some graphs and play around to get some feeling of what kind of oscillations you are going to get if you change the damping constant and so on and so forth. So in the overdamped case, right, so the solution is going to be a combination of exponential functions with negative exponents, so it's going to quickly approach 0. So here is an example. So I suggest that at home you try to solve the initial value problem for the overdamped system. I think it's a good exercise. Then critically damped case is pretty much the same. I mean, only in the critically damped case the solutions approach 0 slightly slower than in the overdamped case. So if you compare the two plots, well, there is hardly any difference. Right? So and then again, I suggest that you try to solve the initial value problem for the critically damped case too. The interesting case is when we have oscillations, right? So oscillations occur when the discriminant of the differential equation or of the characteristic equation is negative. So yeah, this is the discriminant. So it is here. It happens to be negative. So square root of a negative number is an imaginary number. So this is essentially it has plus minus 1/2 something with I. Right? Well, then we're going to have this coefficient that comes from the discriminant is going to appear as the frequency of our of the solution, and the real part, which note is just gamma over 2m, is going to appear in the exponent. Now when you solve word problems, again what you need to do is you just need to extract right values of the constants from the text. So here is an example. I guess it's not too complicated, so let me go through it quickly. So here we have a mass that stretches a spring. So again, you know that stretches a spring 8 centimeters means that we have the L, this L capital is given, the mass is given, and then the mass is in the medium, whatever, in air or water, I don't know, that exerts a resistance of 17.5 Newton when the mass has a velocity of 1 meters per second. And then remember that when we derived the units of this damping constant, then the units were kilograms per second, so you can from here you can deduce that the damping constant should be this 17.5 newtons divided by 1 meter per second, and that's how you know. And then so you have this additional displacement, which is nothing else but just u of 0, and then you can put everything together, converting centimeters to meters. So here is the damping constant. So it is 17.5 kilograms per second. And then you just fill all the values, and here is what you get. right? So then you write down the characteristic equation. Sorry, there is a typo error. I'm going to fix it. Fix it in the printable slides. Okay, so then we can continue. We find the discriminant. Then we can find roots of the characteristic equation. So then we can find the general solution. So here, so this is the general solution. Or we can alternatively write it like this, using the R formula. Well, and then we need to use our initial condition, and by applying the initial condition, first we can we apply the initial value of the displacement, and then we apply the initial value of the velocity, and we know that initially this spring mass system is just released, right? So which means that the initial velocity is 0, and then we're going to have a linear system on C1 and C2, and then we can find C1 and C2. So here is the final answer. Then we can plot damped oscillations and undamped oscillations together. Well, I mean, without damping, of course, what damping does is that it makes the amplitude of oscillations quickly decrease with time. But not just that, so notice that here initially the damped and undamped oscillations, they have a local maximum when t equals 0, but here the next local minimum for the damped case, it occurs a little bit later than the local minimum for the undamped case. And again, it is kind of natural, because, you know, damping makes it slower. So, and for instance, the frequency also becomes slower. Alright, so here is our equation. So then damped oscillations happen when the discriminant is negative, and then the quasi-frequency, which appears inside the cosine and sine functions, is basically, it comes from the discriminant, and the quasi-period, it comes from well, is the quasi-period is going to be the reciprocal to the quasi-frequency, so it's just 2 pi by the quasi-frequency.